Here we'll find the surface area of a sphere, like this sphere here, which is quite a challenge considering that every part of a sphere's surface is curved. Suppose this sphere has a radius r. To get started, let's see if you remember what the volume of this sphere is in terms of r. If you're not sure, just click down here to review. Exactly. The volume of a sphere with radius r is 4/3 pi r cubed. Now let's say the surface area of this sphere, meaning the area of its outer surface, is A. So our goal here is to find an expression for the area A in terms of the sphere's radius r. To find A, let's approximate the sphere's surface as a curved grid with many small squares that all have the same size. The more squares we have, the more accurate this approximation becomes. Suppose these squares are not just on the surface and that they continue into the center of the sphere. If we pull them apart a little, you can see that our approximation of a sphere is actually made up of lots of pyramids. Let's say there's a total of n pyramids that make up this sphere. Let's pull out one of these pyramids and take a closer look at it. In terms of the sphere's radius r, what's the approximate height of this pyramid? Don't worry, this is not a trick question. Precisely. Each of these pyramids extends from the surface of the sphere to the center of the sphere, so its height is approximately equal to the radius of the sphere. Okay, so we said that the surface area of the sphere, which we're approximating as the collective area of all n squares put together, is A. So what's the area of this pyramid's base? In other words, what's the approximate area of just one of these n squares on the sphere's surface in terms of A and n? Excellent. So the approximate area of this pyramid's base is A, the total surface area of the sphere, divided by n, the number of squares in our approximation. At this point, you found the base of this pyramid has an area of A over n, and the height of this pyramid is r. So what's the volume of this pyramid? And to review how to find a pyramid's volume, click down here instead. Right, the volume of any pyramid is 1/3 times the area of its base times its vertical height. So for this pyramid here, that's 1/3 times A over n times r. So we have an expression for the volume of this pyramid. Let's put it back into our sphere. Now this sphere is made up of a total of n pyramids, each of which has the same volume, 1/3 times A over n times r. So what's the volume of our spherical approximation? In other words, what's the combined volume of all n of these pyramids? Right. Each pyramid has a volume of 1/3 times A over n times r, and there are n pyramids, so their total volume is n times 1/3 A over n r. Now this n over here cancels out this n in the denominator, and so the volume of our spherical approximation is 1/3 times A, the surface area, times r, the radius. As we said earlier, if we increase the number of squares in our approximation, it eventually becomes indistinguishable from a sphere. That means the volume and surface area of our approximation should equal the volume and surface area of the sphere. Again, the volume of our approximation is 1/3 times A times r, and earlier you said the volume of the sphere is 4/3 pi r cubed. So when the squares on the surface get really small, these two expressions for the sphere's volume are equal. Now try solving this equation for A to see if you can find an expression for the sphere's surface area in terms of its radius r. Nicely done. You divided both sides by r, so this r goes away, and this r cubed becomes r squared. And then you also multiplied both sides by 3, so this 1/3 goes away, as does the 3 in the denominator over here. And that means that A equals 4 pi times r squared. And there you have it. The surface area of a sphere with radius r is 4 pi r squared. So this is interesting. The area of a flat circle with radius r is pi r squared, while the surface area of a sphere with radius r is exactly 4 times greater. It's 4 pi r squared. Let's try this formula out on a sample problem. Here's a sphere, and suppose its radius is 5. What's the surface area of this sphere? Great work! Let's finish this lesson off with a real-world example that uses this formula. Here's a golf ball. Notice that it's spherical in shape, but it has a dimpled surface, meaning it has lots of circular faces, or dimples, that make the surface slightly uneven. It turns out that golf balls with lots of dimples like these travel farther than golf balls without dimples. Say you want to accurately estimate how many dimples are on the golf ball's surface. You could count them one at a time, which might take a while. Instead, suppose you measure the radius of the ball so you can find its surface area, and the radius turns out to be 20 millimeters. Then you measure the radius of one of the circular dimples so you can find its area, and the dimple's radius turns out to be 2 millimeters. So try using what you've discovered about the surface area of a sphere to estimate how many dimples are on this golf ball. This is a challenging question, so click here if you get stuck and we'll work through it together. Okay, no problem. First off, what's the surface area of this spherical golf ball whose radius is 20 millimeters? Exactly. According to this formula you found, the surface area of a sphere is 4 pi r squared. So that means the total surface area of this golf ball is 4 pi times 20 squared in square millimeters. Great. So that's the area of the entire golf ball's surface. But as we said, that surface is broken up into lots of circular dimples. What's the area of one of these circular dimples, keeping in mind that its radius is 2 millimeters? Right, the area of a circle is pi r squared. So that means the area of each one of these dimples is pi times 2 squared in square millimeters. So the area of a single dimple is pi times 2 squared, and the combined area of all the dimples on this golf ball is the golf ball's surface area, which you found is 4 pi times 20 squared. So about how many dimples are on this golf ball? Here's a cube. Let's give it a little spin. Now cubes have 8 corners or vertices, and let's label them all with purple dots. Now if we look at this vertex up here, some vertices are closer and others are farther away. This vertex, and this vertex are the 3 closest vertices to this one. But which vertex is farthest from the one in the upper left? Exactly, this vertex in the bottom right is farthest away. Let's draw a line segment connecting them. This line segment passes through the inside of the cube, and so it's called an internal diagonal. Suppose this is a unit cube, meaning each side or edge has a length of 1. How long is this cube's internal diagonal? Let's find out. First, let's look at one of the cube's faces, and let's draw in a diagonal for this face. Note that this is not an internal diagonal because it doesn't pass through the inside of the cube. Now we said that each edge of the cube has length 1, and notice that we have a right triangle here. So try using the Pythagorean theorem to find the length of this diagonal along a face of the cube. Excellent. So this diagonal along a face of the cube has length √2. Okay, that's great, but that's not the internal diagonal. So next, let's rotate the cube again. So now the face diagonal is up here and its length is √2. And let's pick 2 vertices that are on opposite corners. So this line segment connecting them is an internal diagonal. Now over here we have an edge of the cube and its length is 1. So imagine we take a knife and line it up with this face diagonal on top, and then we cut down through the middle of the cube. Now we have a rectangular cross-section where the length is √2 and the height is 1, and the internal diagonal is the hypotenuse of this right triangle over here. So using the Pythagorean theorem again, can you find the length of this internal diagonal? Nicely done. So the length of this hypotenuse is the square root of 3. So you figured it out. For a cube with side length 1, the internal diagonal has length √3. Next, let's look at a rectangular prism. Suppose the dimensions of this prism are A, B, and C.
Again, we can label opposite vertices of the prism, and the line segment connecting them is an internal diagonal. To find its length, let's again first look at a face diagonal of the prism. And notice that we can draw a right triangle on this face where the face diagonal is the hypotenuse. So, in terms of A and B, how long is this face diagonal? Precisely, so the length of this face diagonal is the square root of a squared plus b squared. Next, let's look at the triangle formed by the face diagonal, the internal diagonal, and this side down here of length c. Sure enough, it's another right triangle where the internal diagonal is the hypotenuse. So, in terms of A, B, and C, how long is the internal diagonal of this prism? Excellent! So the length of the internal diagonal is the square root of a squared plus b squared plus c squared. So this is the general formula for the length of a rectangular prism's internal diagonal. Pick any two opposite vertices, like these two, or these two. Every internal diagonal of a rectangular prism has the same length, and to find it, square the three dimensions, add them up, and then take the square root. Try a numerical example. Suppose this rectangular prism here has dimensions 9, 4, and 12. How long is each internal diagonal of this prism? Nicely done. So you took the three dimensions, and then you squared them, added up those squares, and took that square root. This equals the square root of 241, which is approximately 15.52. So because there's a square root right there in the formula, a square root that comes from the Pythagorean theorem, you'll often get square roots in your answers. But sometimes the numbers work out nicely. So finally, find the length of an internal diagonal in a rectangular prism whose dimensions are 2, 3, and 6.